Hello, welcome to today's lecture. Um, so here's the deal. We have, I believe, 7 lectures left. The most important thing that I'm going to say today is that at this stage, you should have picked your project kind of topic, i.e. data set, and ideally model architecture. So you're going to need a couple of weeks to to develop your scripts, to develop your tests, generate figures. And so I don't want it to be a unpleasant experience for you guys. And so right now is when there's a ton of data sets available. I think I linked to kaggle.com. Google has a data set search, which is really cool. Hey, and there are others. The historical database repository is the University of California at Irvine, the UCI database. Those are like the older type, but classic data sets. You can also find stuff there. Kaggle is amazing. You can, it's very interactive. So on Kaggle, people will go on and not only upload data, they'll also upload their code. And so, see if I can demo it. We'll go on Kaggle. Zoom messes up my window management. So we'll go to kaggle.com. And let's say I'm interested in, COVID. Okay, so coronavirus visualization and prediction. And then you'll see that you'll be able to actually, it's very recent actually. You'll be able to see that they have code pasted for you so that you can, this is really powerful in the community. You can go on and you can not only access the data that they've posted, you can also see how they've used pandas here to, I guess, organize their data and show you their data, and there's some analysis coming down below. Point is that the project, you should be able to perform the project by essentially, I don't want to say copy and pasting, but curating different pieces of code and hopefully modifying those pieces of code to do something new. But starting early is important, just so you have your data set picked out, and that you have the data set loaded, and like you can train like a base model on it. That will give you kind of the peace of mind to know that in the final 3 weeks of the course, you'll be able to do the required analyses and put together a presentation. So the other important thing, the last day of class, which I believe is the 16th of May, will be the presentation. So everyone who is registered in the class has to present. I believe that we should be able to try to get through all of them in one class. We may go over, but hopefully that's okay, given that we're not doing a final exam. And if we need to, we can use Wednesday, the final exam day, the 18th. And so I have a little script that I run to randomize the order of presentations, and each of you will present your findings. So again, the project is kind of the most important part for me of this course. Oops. I don't want to open up that one. Okay. All right. So what I'd like to do is to show you how to build a very basic model in Keras and how to use it to make predictions on a data set. So I have posted this to Blackboard. Hopefully you're able to download it and ideally run it, in your Jupyter notebook, you can also just copy and paste the code into an editor such as Spider or PyCharm or Visual Studio. So hopefully you guys all have a TensorFlow Keras set up at your disposal. It will make this a lot more interesting for you. So this first cell is a standard preamble. We have to import all the libraries that we're going to use. So we need libraries for bringing in data. So I have the data saved as a MAT file, and there's a lot of interoperability between MATLAB and Python. So the scientific Python, whatever library, SciPy has an IO package that lets you bring in MAT files and loads them into a Python dictionary, which I'll show you in just a second. And the rest, NumPy's linear algebra and TensorFlow and Keras, well, you know what those are. So we're going to run this cell. So you moved on to the next cell, which means there's no problem. And here's a step where we're going to load in our arrhythmia data set. I'm using the data set that I prepared for the midterm. I'm going to run this, and I printed out the contents of variable mat contents. So mat contents is a Python dictionary. So what is a Python dictionary? It is it's a convenient data format where you have pairs of labels, not machine learning labels, like string labels with a colon, and those string labels are encased in single quotes, and then a colon, and then you have the variable, the contents of the variable. So Matt, the important elements of the dictionary are X-test. So X-test is your training set features, and you have X-train, then you have Y-test, and you're going to have Y-train below. And so the way to access the elements of a Python dictionary is to use this notation. So this is like indexing into an array, except that the index is a string, and that's your label. So now what this first line says is that go into the dictionary whose name is mat contents and pull out the element called X-train and assign that to now a variable called X-train. So this is really convenient. That's one of the things that makes Python so popular. They have these very high level syntaxes available for packaging and accessing data, different data, heterogeneous data. So now, I guess what I'll do is I'll just show you the shape of the variables that we pulled in. Just to always need to look at the size of our arrays just to know that we have what we need to train our model. Oh, it only prints out the last one, so I have to go print. It's like this. So remember, the convention in Keras is to put the examples on the first dimension and then the features in subsequent dimensions. And the features in this case are just, they're like vectors. Sometimes they can be images or even tensors, hence the name. Okay, so here, this is the shape of the variables that we've loaded. And we have oh, this is wrong here. Yeah, thank you. Yeah, so there we go. We have 289 examples in our training set. We have 141 examples in our test set. These are our labels. And I think I can show you, let me see if I can show you print. See if this will work. NumPy. Always want to look at, I don't know if this is going to work. We'll see. There we go. It does. So it shows you that your labels are coming into you as either zeros or ones. Okay, so hopefully if you're following along, you've made it to this point. If anyone needs me to pause or needs me to troubleshoot your code, let me know. Again, I hope that as many of you as possible are able to follow along. So the next line, the next cell is the most important one. This is where you specify your model. So what I'm gonna actually do first is this is not the most basic. The most basic I'm gonna put here. I'm gonna comment out the later step. So we're just gonna actually have one layer here. We're gonna make the most simple model possible. So what this line is saying, this is a line that's one line of code that spans multiple lines in the editor. So model is going to be the model variable. It's an object of the sequential class in Keras. So sequential is the most common type, it's in Keras's API, and it's the most common one because you literally it's called sequential because you just literally add model components one after the other. So starting from the input all the way through to the output. Now, Keras is smart. They don't even need you to tell them what the input is going to be. It can figure out the first time you call fit, it will look at the size of X train, and it will figure out what the input shape is. So they don't even impose that on the programmer. You can just say my model is going to have one dense layer. So what is a dense layer? It's a fully connected layer, which means that there is a connection between, in this case, between every node in the input and every node in the output. Now, this number 1 here is the number of outputs, right? So this is saying make a dense layer that has one output. And because this is the first layer, you know that the input that it's connected to is the input layer. And then the next, I think there's 2 required arguments. The second required argument is the activation function. And we're going to use a sigmoid activation. Why? Because we're predicting zeros and ones. We're predicting scalars. So it's just the sigmoidal activation, same as in logistic regression. This is an optional argument. So I've put in a little bit of regularization, and just to show you how easy Keras has made it, there are different types of regularizers, and if you want to look at them, just search. If you search Keras regularizers, you'll get to the API, and it will show you all kinds of, basically this is the website that I have spent a lot of time on. And most beginners to machine learning spend a lot of time on. It's the Keras API, super well documented, lots of examples. So this page will show you, for example, the different regulators. We have an L1, we have an L2, and we have L1, L2. Is there anything else? I don't think so. You can do a custom regularization too, if you're up for that. But we're using the L1, L2 because I want both types of regularization in here. And so these are the lambdas, these are the hyperparameters. So these are values that you kind of have to tune. We're not going to tune them here for obvious reasons. We're just going to handpick them. And so for an example like this, where we're just demonstrating how to fit Keras models, perfectly fine to do this. Obviously, if you're going for optimal performance, you'll want to choose these in a data-driven way. So, okay, so basically the model is specified by the layers, and this only has one layer, and that's the output because the input layer is implied. And so I'm going to run this, and hopefully I get no problems and I don't. So now I have my model built. So now I may be able to print out, I don't know if I print out model, what says anything, not much. It just tells us that there's a variable at this location in memory. So I have to compile this model. This is one difference between what happens in MATLAB with SVMs and logistic regressions versus what happens in Keras. In Keras, you actually have to compile the model. What that means is that you're you're preparing Keras to accept data, essentially. So you need to endow this variable model with some additional features that are going to allow you to train that model. So right now the model has the architecture, but it still needs other information. For example, what is the loss function? So we're going to use what's called the binary cross entropy loss function. So this is the most common loss function for binary classification. It's a fancy term. Essentially what it means is you want the positive examples to have a large probability, and you want the negative examples to have a low probability. That's it. It's like the negative log likelihood in logistic regression. Other popular choices for this are something called categorical cross entropy, which is the same thing, but you have multiple classes. If you really want it, you can do mean squared error. And there's a bunch of different losses that you can choose from. Again, if you go on the Keras API under losses, it will show you the different options. You can also define your own loss function. The optimizer, Atom is kind of a, how should I say it? It's a special form of stochastic gradient descent. Again, you're trying to get to the bottom of the hill, and Atom is just, it accelerates the process for you. There are step size adjustments and things like that. And then the metrics. I don't think you have to specify the optimizer. I think this is the default. And then the metrics is just you need to tell the model what you're interested in measuring for your performance. And so here we're just going to stick with the simplest possible metric, namely accuracy. So so we're going to run this cell. The cell ran, believe me, because it didn't give you an error. So now the model is compiled. And so now we're ready for the key step. This is the core step. It's where you actually fit your model. So you give your model training data that is then used by the fit function to tune those weights that we defined here, the dense layer. So what are the arguments to fit? Well, obviously we need X train and Y train. You need something to train on. Batch size is, so stochastic gradient descent doesn't take all the data at one time. And this is really just coming out of the fact that in deep learning, oftentimes the data sets are huge, millions of examples. And so it's slow to take the entire data set and compute the gradient, and then on the next iteration, compute the gradient again, et cetera. And so what they do is they use these what are called mini batches, which is you take a subset of the training data, you compute the gradient on that, you update your weights, and then you go on to the next batch, the next batch, and the next batch. So we're not going to do that. We're just going to say, you know what, take my entire training set as one batch. And so I had 30 epochs here, but let's actually bump this up. Let's go to 100. Let's see what happens. Validation split. Keras has this neat little argument where you can tell it to hold out 10% of the data in this case and use it to measure the loss or the accuracy on that held out data. So it's kind of like a way of getting generalization performance to you, communicated to you while you're training your model. This actually probably isn't a good idea in our case because we only have 289 training examples. We don't want to cut into those, but I'll just run it like this to start and we'll see what happens. So you're going to see with every epoch, you're going to get a loss value and an accuracy value. So here comes let's see, it ran, and we'll see what the accuracy ended up at. So the validation accuracy ends up at 72%, and the accuracy on the training set ends up at 71.5%. So I believe that those are quite high compared to what we saw in MATLAB on this data set. So for example, if you track these values from the first epoch, you see it starts out at 0.5. Those are when the weights are all 0. And then it starts growing. And then at some point it will start to kind of plateau. and that's when you can stop your training. So now I have my model fit. My model is now ready to make predictions. So there's two main ways of making of kind of testing your model. One is one is the evaluate function, which I'm using here. The other, there's a function called predict, which is very related. The evaluate method is nice because it actually tells you, it outputs the actual metrics for you. So the metrics that will output are the loss function and also the accuracy. So first I'm going to measure the metrics on the training data. I do this as a sanity check to make sure that something is being learned on the training data, which it should be. If not, there's something seriously wrong. And so we have that the accuracy on the training data is 72%, which you saw up here. That's very good for this data set. And now the most important step, this is the step where you're kind of anxiously awaiting what the number is going to be. This is where you actually evaluate your data on the test set, the unseen data, and you measure its performance. So again, evaluate on X test and compare to Y test. And so 65%, not bad. I mean, I don't think it's much higher than what we saw in MATLAB. I also think we got unlucky with the stochastic gradient descent. I bet you if you run this again, so I'll initialize the model again. Although I don't know, maybe fit it again. Okay, unlike MATLAB, Keras is super stochastic. So every time you run it, you have to go to great lengths to get the same numbers out. Oh, even worse, 58% this time. And so I wonder what if I put in validation split 0? Let's see what happens. So here I did not put any validate. I'm using all the data to train. Oh, higher training data, higher training performance. Still only 65%. So I'm going to make the next tweak that I'm going to do will hopefully increase the test accuracy. Okay, so this is I mean, that's what I've shown you is basically the process of the process that you go through in Keras when you are working with a data set. What I'd like to do now is actually first I want to show you that I could have done the same thing. I forget what it's called. Input. I think it's called shape. Let's see if this will work. I'm guessing on the. So if I wanted to, the main what's it called? The main benefit of adding input layer is that then you can print out a little model summary of your model to show you exactly, oh, what's wrong. Oh, comma missing. Okay, right, so this is what I was going for. So now you can see that the model summary is something that you look at often just to show you how many parameters you have. So the reason that we have 275 parameters is because we have a 274 dimensional input layer. And then we have the one bias, the one intercept term. So we can do the same thing. We should get very similar results with this model. So I'm going to compile and I'm going to fit. Let's see what it went down to. And then the training performance is 64 and the training performance is still 65. So you see how stochastic this is. Every time you run it, you get a huge difference. There's a couple of things that you can do. One thing is you can make the batch size smaller. So you can, let's say you make the batch size 64. So now you're only using 64 examples per gradient computation and see if that helps at all. Training performance. And so this is the highest that we've gotten so far. And we got the 72% and by using these mini batches. So and this is very confusing to people, I think. So an epoch in Keras means one pass through the data. So as we have 200 and what is it, 289 examples, I think, in our training set. So, and we have 64 examples in our batch. So what Keras is going to do when fitting is it's going to take 64 examples at a time. And then when it's included every example in a batch, it will move on to the next epoch. So the next epoch is like you're restarting the gradient descent, and you restart wherever the last one. Actually, no, I think you restart. Let me think. Do you restart where the last one? Yeah, I believe you restart where the last one went left off. Okay. So this is, and then epochs is so choosing the value of batch size in epochs, it requires you to consider how big is your data set. So if your data set has 1 million examples and your batch size is 64, you're not going to need as many epochs because every epoch is already going to have a lot of updates. In this case, we only have a few batches per epoch. So that's why I've gone up to 100 epochs when fitting this. There shouldn't be any harm in having a lot of epochs. I can make this 1,000 or even higher. There is something called early stopping. You can look into that. Early stopping is where you explicitly tell the fit function, do not get all the way down to the bottom, because I suspect that if you get down all the way to the bottom of some hill, you're actually overfitting. So early stopping is a way of getting to a nice local minimum, but not necessarily the lowest, because sometimes the lowest minimum is just some fluke in your data set. Okay, so the other thing I wanted to do in the demo is now add another layer. So we're going to add a hidden layer, which is very important. So, okay. So now there's my input layer. And now I've added an intermediate layer that's going to have 10 hidden nodes, right? So there's the mapping here is from our input layer, which has 274 nodes, up to the hidden layer, which has 10 nodes, and then finally a dense layer. So we should have something like 2,740 weights for the connection from the input to the first layer, hidden layer, and then we should have another 10 weights for the connection from the hidden layer to the output. So we should have something around 2,750. We're going to see. We're going to compile this. Hopefully we'll compile. So 2,761 when you include all the intercept terms. So notice that I've chosen a different activation for the hidden units. So this is ReLU is this rectified linear unit. I think I showed it to you on an earlier slide. It's very popular because it looks like the linear function if your output is positive and it's 0 otherwise, which makes gradient descent work really well, kind of loosely speaking. And so the output of that ReLU is gonna feed our final output layer. So our model is gonna, we're gonna have 274 those nodes at the bottom, then 10 nodes in the second row, and then just 1 node on the top row. Now 1 node in the top row has to tell us whether this is an arrhythmia example or a healthy ECG. Okay, so we have this model specified, and now we're going to compile it. And now I'm going to fit it, and we're going to see, I at least expect the training loss to be lower, because now I have more parameters. I should at least be able to get the training loss lower than before. So let's see where it ended up. I may have to. Yeah, so this is probably going to be overfitting. We'll see, but you see that the accuracy shoots up, right? This was a very difficult data set. This is a data set that in MATLAB we are getting 60 to 65% on. And then training scores, very good training score, 86%. And the moment of truth, 68. It's not bad. It's actually not bad considering that, you know, we only have 289 examples and like 2,700 parameters. One thing I like to do in these situations is you can play with more, I haven't tested this at all, but we'll do it now. We'll add, instead of having, we'll add 2 hidden layers, but we'll make them smaller to not blow up the parameter, to not blow up the number of parameters in our model. Okay, so here it shows you this is the first hidden layer. Is that right? Right, yeah. So this is the layer this is the connection between the input and the first hidden layer. This is the connection between the first hidden layer and the second hidden layer. And then this is the output layer. It's just 5 to 1. And so now we're at 1,400 parameters. So let's compile this and see how we do. Okay, so the loss is really low, 0.68. So our accuracy here, our training accuracy is 87% or 88%. And then again, the moment of truth on test set, 79%, that's excellent. There you go. Prove that deep learning, there, you know, it's not, I'm actually surprised that it went that high.
Professor,
Yeah.
can you explain the loss? Like, what kind of values are we expecting for loss?
Yeah, it's a good question. It's between 0 and 1. So basically 1 is like a perfect model. Oh, sorry. Let's see. Binary cross entropy is the negative log likelihood. So, okay, no, let's see. I believe that 0 is the best model. And let me actually see.
Your training is lower.
I think we had a loss before that was more than 1, so I don't think it's between 0 and 1.
Yeah, sorry. I think, yeah, it's lost. So it has to be, you can actually, you know what, you can actually, let's see what it starts out at. Yeah. Yeah, so it's something like, can I put a comment here? Yeah, markdown. So binary cross entropy is something like, let's see. How do I do this? I believe it's this. Okay, so what does this mean? So when given x, you know, why don't I don't need, I can show you the equation. I'm sure Wikipedia has a, no, I don't want to. There. So it's the log of what, right? It's this thing. So it's the log of what I was writing. And so let me see if I can pull one up that is, okay. Okay, so oh, can't get away from you towards data science. Here we go. So what does this mean? You want the positive examples to have a high probability and you want the negative examples to have a low probability. Where this gets tricky is that the log, so the log of a probability is always negative. And that's why you stick this negative sign in the front. The summation is over the training set. And so yi here is either 0 or 1. So basically, okay, so here's something. Let's see if I can annotate this. So for a given example, either this is going to be 0 or this is going to be 0. So if the label of example I is 0, then this thing comes out. Okay, that term is 0. And now this term here just goes to 1, right? This term goes to 1. And so all you're left with is this. And so this is the case where yi is 0. When yi is 0, you want, let's see, what is this going to drive? This is the minus log of 1 minus p. So, right. So this is, you're going to want to drive this thing to be equal to 1, because you're trying to make the argument of the logarithm as close to 0 as possible. So you're trying, so remember that our label was 0. And so you're essentially making the probability of 0, that y is equal to 0, given x. You're trying to make that as close as possible to 1. Why? Because when this is as close as possible to 1, this is the log of a very small number is very, very negative. And then when you, no, hold on a second. That's going to be backwards because this is loss function. You're trying to minimize this.
You want to be as close to 0 as possible, I think, because log of 1 is 0, but log of 0 is infinity.
Yeah, the thing is that this is, remember, this is loss function. So you're trying to minimize the loss. So you're actually trying to minimize this thing. So let me just.
Right, so if your p of y equals 0, then log of 1 is 0. That's what you want. You want the whole thing to be 0.
Right. That's right. That's right. That's right. Exactly. Thank you. Thank you, Andrew. Exactly. You want the argument of the logarithm to be equal to 1. Because that's what's going to make this as small as possible. And so you want to make p of y is equal to, you want to make the probability equal to 0. This is actually good. Let's actually work through the two cases. I'll use text for this. So if yi is equal to, let's take y is equal to 1. Then this term will come out, right? This term comes out. This goes to 0. And all you're left with is here. And so you are going to try to make, this case is easier to understand. You're going to try to make this equal to 1. So you're trying to drive p y given x equals to 1, essentially. So you're trying to make the label equal to, you're trying to make the label equal the target. You're trying to make the target equal to 1. Okay, so that's the case where y is equal to 1. And then now the case where try this again, yi is equal to 0. Then this comes out. Right. This becomes 1. And then you want p this notation is confusing because
But
why?
you're gonna want PYI to be 0.
Yeah, no, I know that, but this notation, if PYI, it's like you want, why would you want, hold on, PY is equal to 0 given X. If you want, so if yi is equal to if y is equal to 0, so the label is 0, so we want this, I mean, we want this to be high, obviously. So maybe this p of, we want this to be low because the label is 0. And so, oh, I know why. It's because this is equal to 1 minus p, because the probabilities have to sum to 1. And so by, if you, wanting this to be close to 0 is equivalent, sorry, wanting is equivalent to wanting this to be as close as possible to 1. Or sorry, wanting this probability to be as close as possible to 0 is equivalent to wanting this probability as close to 1, because the two are complements of each other. So but getting back to the original question, what the loss function here, it's essentially a log probability with a negative sign. And so the it's actually unbounded. It could be infinity. Go back. So if you had a really bad model, then the cross entropy, if you had a really bad model, then this is log. This is logged. A really bad model would make this equal to infinity, and a perfect model would make this equal to 0. And it has that kind of logarithmic shape to it. Okay. Let's see. Any questions before I continue? This is yeah, I mean, essentially this is where the decisions come in what I've highlighted. This is where you specify your architecture. And so people will play around with the size of each layer, and they'll play around with the activation function, and they'll play around with their regularization terms. Other than that, you know, there's not much, there's not, and the batch size, I guess, also. If you use a smaller batch, we can just try running this. Smaller batch size, the gradient is more stochastic, but you're letting your model, yeah, you get slightly better performance. You get a lot, 79% accuracy. So the smaller the batch size, the more random your gradient computation is, because you're not looking at all the data. But some people view that as like a nice thing, in that you're kind of, the term they use is they're exploring the parameter space. That's why they like stochastic gradient descent, is that you're looking at parts of the parameter space that you wouldn't necessarily look at if nothing was stochastic. All right, so I do want to, I guess I'll just start with lecture 10, slide deck 10. So what I'd like to do in terms of like the content, I called this 10, I think it should be called 9. I just want to talk about convolutions for the last 10 minutes. So in terms of like the key types of networks or layers that people use in modern applications, they use obviously fully connected layers, especially when you're getting close to the output. They use convolutional layers, and they use something called LSTM, which is long short-term memory. That's for time series data. Convolutional layers, convolutional nets are, I guess you can say they revolutionized machine learning. And they were invented by, or at least popularized by Yann LeCun, who was at NYU. And the basic idea is that when you learn patterns from data, you do not need to, you don't actually need to give every pixel its own weight. That's kind of the easiest way of saying it. You recognize that if you're looking for an object in an image, you don't know where that object is exactly, but you can kind of learn a template for that object. You can kind of learn a texture for it. And so what convolutional networks do is they use what are called kernels or filters, and they slide it across the image looking for your objects. And the big benefit of that is that kernel has let's say it's a 2x2 kernel, 2 pixel by 2 pixel. It only has 4 weights. And then those 4 weights are scanning the entire image. And so even if your image is very large, you don't need to use a huge number of parameters to run your object recognition algorithm, your model. And so the diagram here, which I'm not expecting you to understand at this point, is just it's a schematic of what a typical convolutional network looks like. So we have our input image, which is usually 2D, and then we apply these convolutional operations to the image. And basically, as you go from input to output, the image or the projection of the image is getting smaller and smaller and smaller. And the idea is that you're looking for these objects, and as you get closer towards the output side, your network has a more abstract representation of your image. It's no longer the pixel values. It's like, is there a face? Is there a cat or something? And those abstract representations kind of come out over here and flatten the data. And so, for example, this is an example of a multi-class problem where it's object classification, where you're categorizing between cars, trucks, vans, and bicycles. Okay, so let's try to unpack that. So you probably have heard of convolutions if you've done an undergrad in engineering. So this is the equation for a convolution. And so S is your input, and Y is your output. And H is called your kernel, your filter. So in one dimensions, what this is doing is it's literally just filtering your data across time, in this case, if T is time. And so at every time point, your output is kind of a linear combination of the present sample, that's when tau is equal to 0, as well as past samples. So what this equation is modeling is that your output is a linear combination of many inputs at different time points, which is what filtering is. You can also write that in 2 dimensions, in discrete time. So now K is a discrete integer. And so this is the same equation, just that the integral has been replaced by a summation. So again, at time K, your output Y is a linear combination of your input S, and every different time delays, K, have a different coefficient. And so if you make HK look like a sinc function, this is a low pass filter. I think a high pass filter is closer to high pass filter is like 1 and then -1. It's like an edge detector. And so now what about in 2 dimensions? Because we're dealing with images. So it's the same, conceptually it's not different. You're still just doing you're still just kind of integrating across different portions of the image. So M here is like your row dimension, and N is your column dimension, and I is your image. So this says that the image output, which I'm calling at capital S here, is defined as the two-dimensional convolution between a kernel K and an input image I. And so it's just, don't let the two-dimensional summation scare you. All it is, it's now you're taking the image and you're applying some two-dimensional kernel across it, and you're essentially multiplying it point by point with your image, and then slide it across, multiply point by point, and you keep sliding it across, and the output image is the summation. So important is that you have to do, for every pixel ij, you have to perform this summation. That's important. So every pixel of output image S is this two-dimensional integral over your input image. And generally K is smaller than I. K is usually a smaller size or support than image I. So the nice thing is that this convolution can be this convolution can be written as a matrix multiplication. And so here I'm just showing you some basically what a matrix product is. So you could, if you have an M by P matrix, so you have 3 rows and 4 columns, you can think of that as a 3 by 2 matrix multiplied by a 2 by 4 matrix. So why is this useful? Why? Because this is kind of reminiscent of the singular value decomposition. Now you're decomposing your original matrix into a sum of submatrices. So in theory, we could have M just be 1 column and N be 1 row, and we could still get a 3 by 4 matrix here. However, that will be what's called a rank 1 matrix, where it would just be an outer product between a column and a row, which wouldn't give you a lot of diversity over the values of this image, which we're calling here by C. So what every column in M and every row in N does is it gives you one more kind of dimension in your matrix. And so remember that the number of columns in this matrix has to matrix, let's call this matrix A, has to match the number of rows in matrix B. And so what this is saying is that an image can be factored into a product of smaller matrices. And then another thing, there's a lot of when you perform convolutions, you're doing a lot of transposing of matrices. So one thing that this is from the Goodfellow book that they point out, that transposing a matrix, you probably know that transposing a matrix is equivalent to taking its rows and making them columns. But another way of thinking about it is that you're kind of reflecting you're reflecting your array along the main diagonal. So if your main diagonal is here, notice that the elements have kind of been reflected along that axis, if that makes sense. Okay, so yeah, I'm going to stop here because this is an important slide just so you understand what a convolution is, but we'll pick up here on Wednesday. Bye-bye.